So today we will study Hamiltonian system. So once again, this type of system that may be hard to solve analytically, but any problem that has this structure, shares some nice property that I don't need to solve it to know this. And this is the same for gradient system that we cover in 9.3. So here's how a Hamiltonian system look like. Of the following form. So once again, if there is a function that we call h, so that x prime is dh dy, and y prime is dh dx. And I can give you some examples that falls under this category. The first example is what we know in ODE class, what we call undamped harmonic oscillator. Now, second order ODE looks like this. The displacement of the spring, x double prime, plus kx, where k is the spring constant. Undamped, so there is no friction, there is no external force. And we can write this into a system. We'll let x to be the displacement. So y is x prime, which is essentially the velocity. And y prime will be, acceleration equal to negative kx. So this is the only external force coming from the spring. So let's see why this is actually a Hamiltonian system. In other words, what is the h that make the right side is dh dy? Obviously, I need something like 1/2 y squared, isn't it? And dh dx has to be kx in this case here. So the second component will be like k over 2x squared. You can pause for a minute. You can verify that dh dx, which is in this guy here. So this system right here is Hamiltonian system. Example number 2. Any conservative system. Any conservative system. I guess we're referring to that there is no energy that's going to be lost. Similar to the undamped harmonic oscillator, the conservative system looked like this. Okay, x prime is y, and y prime turns out to be, just a function of x. Any function of x. So in the previous example, it's negative kx. So the h in this case is given by 1/2 y squared, and the minus the indefinite of little f. All right, so this will give you the function h. H, by the way, is called Hamiltonian function. Okay. So one more example. Let's look at this system. So f of x is given by this formula here. Let's write down what my h is. 1/2 y squared minus indefinite of this one here, which you can easily integrate this out. So all of those examples that I provided, these are all Hamiltonian system. So the question is, in general, how do I tell if a system is Hamiltonian or not? So the general question is, how do we tell that a general system that's in this form is Hamiltonian or not? All right, and this turns out to be not too hard to answer. So essentially, for this guy to be Hamiltonian, this one needs to be the derivative with respect to y, and this one needs to be negative dh dx. So I need f to be dh dy, and g needs to be dh negative dh dx. All right. So what kind of condition f and g has to met and to make this Hamiltonian? And notice if I differentiate f with respect to x, I will get second derivative of h with respect to y and then with respect to x. So this is a mixed derivative. Now, which will be the same as negative differentiate g with respect to, well, y. This will give you another mixed derivative where it's going to be identical to this. So this is the single criterion that we're going to use. So right here, okay, folks. If f and g satisfy this, then it is Hamiltonian. Next, if it is Hamiltonian, how do I find out the function h? So once again, I need the h dy to be, well, f of xy. How do we find out the h? What is h? How do we find it? Obviously, I can directly integrate on both sides with respect to y. I get in-depth integral of f of xy and integrate this with respect to y. Now, obviously, the derivative of this guy, okay, with respect to y will be f of xy. Notice if you add any function of x, okay, you differentiate this guy with respect to y, you also get you get a zero. This guy here. So h in general will look like this, but the question is, what is the h here? What is the h? To find out h, notice that I also need dh dx to be, can you think about that? Dh dx needs to be negative g, okay, negative g. So I'm going to differentiate this guy with respect to x and set it equal to negative g of xy and try to figure out h here. So h is this one. I'm going to differentiate this with respect to x. So I can actually differentiate this integrand. Differentiate h with respect to x, I get h prime. This needs to be negative g of xy. So the key here is we're going to use this equation here, okay? Use this equation to find out h. Find h. So basically, to figure out h, you got two steps. That's the first step, and that's the second step. The second step allows you to figure out what h is. Let me show you an example here. Let's look at this system here. Is this Hamiltonian or not? And how do I verify this? So this is the f, this is the g, okay? That's the f, that's the g. How do I verify this? Going back to the criterion that I gave you a little while ago. So I need to do df dx, and it needs to satisfy this. All right. So df dx, which is obviously, well, just 1. Does that equal to negative dg dy? Dg dy is negative 1. Dg dy is negative 1. And that is indeed, put a negative sign in front, that's indeed 1 as well. So this condition is met. That's why this is Hamiltonian. So it is a Hamiltonian system. The next question is, what is H? Or how do we find H? Okay, so let's try to find H. To find H, so if you look at the form of Hamiltonian system, dHdy has to be F has to be this guy. So obviously you don't have to memorize the steps that I told you. You will know what to do after this. You will integrate on both sides with respect to y and followed by an unknown function of x that we need to figure out. Integrate this with respect to y, you get x times by y. Okay, treat x like a constant. Integrate this, you get y squared. And h of x is something that we need to further decide. And then from the second equation, I have partial derivative with respect to x with a negative sign in front. That'll be the same as negative y. So let's see what kind of x will satisfy this as well. So differentiate this with respect to x. We get negative y plus 0 actually, and the h prime of x. That needs to be negative y. Those two guys obviously cancel. There's 0 here. So h prime of x has to be 0. So what do you think h of x is? It's actually any constant c. Okay, any constant c. So put it simply, the function h that we just found is, okay, the Hamiltonian function for this system is okay, that's the Hamiltonian function here. So now we understand what a Hamiltonian system is, and we understand how do we verify whether a system is Hamiltonian or not, along with how do we find out Hamiltonian function here. Next, obviously, we want to talk about what kind of property Hamiltonian system has. Okay? So the first results about Hamiltonian system, any Hamiltonian system, is the following property. H, okay, Hamiltonian function, turns out to be always a constant along every solution curve. Okay? We want to prove h is a constant. It doesn't matter how your time changes. We want to prove h is a constant. All right. To prove h is a constant along every solution curve, here's what we do. We do the time derivative. I want to show this is always 0. Chain rule. Chain rule. There's nothing I can do about those two terms, but dx dt, however, dx dt satisfied the equation. Okay, in other words, x prime is dh dy, y prime is negative dh dx. We're going to plug that in. Sorry, that's a y here. So this is the product between dh dx and dh dy. This is the product dh dx dy and dx dh dx with a negative sign in the middle, which is obviously 0. Yeah. So it's that simple, okay? It's that simple. Hamiltonian system is h is always a constant along every solution curve. I'll show you one example. Example 5. This is a conservative system, as I showed you earlier. And H is, that's H, okay? That's H, plus any constant C. H is a constant along every solution curve, okay? In other words, every solution curve will be the level curve for H. You know, H is a constant along every solution curve, so solution curve will be its level curves, the same as the level curve. Will you try to sketch a level curve for H here? All right, I suppose you can use any online software to figure out level curves. And it looks like this. Okay, here's -1 and 1. This level curve. It turns out this is also the trajectory. Okay, this is also the trajectory or phase portrait of that system. This system right here has 3 equilibriums where y is always 0, but x can be -1, x can be 0, x can also be 1. So these are 3 equilibriums. So there are some closed orbit around those 2 equilibriums. And notice this special guy here. Actually, direction look like this. This solution curve actually connects. Okay, actually connects this equilibrium solution with itself. Okay, it's come back to itself. For a solution curve like this, for a orbit like this, we call this homoclinic solution. Every time it connects an equilibrium with itself or come back to itself, we call this homoclinic solution, or orbit, or trajectory. Okay, these are the same concept. Okay, same concept. So the level curves, okay, for Hamiltonian function will be the trajectory or phase portrait for the Hamiltonian system. That's what this theorem, okay, this property is trying to tell you. Okay, so that's that. The next property is about the linearized system. Okay, it's about the linearized system. Proposition. Let's say Hamiltonian system has this as an equilibrium point. For a planar system, sorry, I should say this Hamiltonian system, okay? Then turns out the linearized system has either positive or negative lambda. Positive or negative lambda, meaning that equilibrium will be a saddle, or a pure imaginary eigenvalues. All right. And let's take a look at why that is the case. Similar to the gradient system that we studied in 9.3. This proof is also straightforward. Let's look at the Jacobian, okay? The Jacobian. Hamiltonian system look like this, okay? Hamiltonian system look like this. Let me show you Hamiltonian system. Hamiltonian system. We're going to take this term differential with respect to x and then y. So you get a mixed derivative here, and the second derivative with respect to y. Same story for this guy, differential with respect to x, second derivative with respect to x, and then a mixed derivative with respect to x and y. Once again, those two guys are the same. So I can call this number a, and the number down here will be negative a. Call this b, and this will be c. In the same way, we write down the determinant of lambda I minus j. You see, there's no lambda term. All right, there's no lambda term. That's minus a squared and the minus bc. So lambda squared will be a squared plus bc. If this guy is positive, if this one is positive, we are talking about positive or negative lambda, so real eigenvalues. If this guy is negative, if the right side is negative, you are talking about a pure imaginary number as the eigenvalue. In the textbook, well, unfortunately, you can't see it. There are some exercises, and this is on page 213. I want you to dig out that out. There is a problem like this. So, I mean, by the way, this is the end of this lecture, 9.4. Okay, and the rest is I'm trying to ask you guys to do some exercise. So write down the following problems. Is this Hamiltonian or gradient system? How about this? The condition I already gave it to you guys, so try this out. There are some exercises at the end of this chapter. This is the end of chapter 9, by the way. Okay, the global techniques. So make sure you review some additional materials. But otherwise, I'm done with the lecture for this part. I'm trying to keep this short because I don't think an hour-long video you guys can stand it. So that's the end of 9.4.